Greetings. Hi, Stephen. Hello. Hello. Hello.
Hello. I was just going to pick up the phone and call you. Okay, hold on 1 second. Oh God, this stuff goes so slowly. Well, so you've got some exciting stuff. Okay, hold on 1 second here.
Yeah.
I'm trying to figure out what to say about this Euclid graph. And I was trying to argue that it's sort of a coherent knitting together. See, this graph is somewhat more microscopic and consists of all of the proofs. There are the axioms of Boolean algebra, at least I think they are, at the top. And these are the knitted together proofs showing the common, showing what's in common and what's not in those proofs.
Mm-hmm.
I mean, it'd be better if the things were turned around so that they actually were generating those things as output, but it is what it is. I guess we could do cut elimination. Could we? No, we don't want to do that because we want to show the common theorems. But this would be nice to be able to turn around, if you understand what I'm saying, so that the theorem comes last.
How can we turn it around?
Well, so it isn't doing the theorem proving thing. So it's doing the, okay, anyway, so the question is here, and then I was going to come to your stuff. The question is here, what do we conclude from this? Because here's an amusing fact that 55% of all the theorems in Euclid depend on all 10 axioms, and 64% of the 11 notable theorems of Boolean algebra depend on all 6 axioms.
Mm-hmm.
The question is, what on earth do we conclude from this? And I was trying to understand, one thing we could conclude is what the distance matrix is. In other words, what, you see what I'm saying? Because the distance matrix, I mean, we could even make this graph bidirectional and look at the distance matrix, and that's in a sense showing how knitted together the whole thing is, if that makes sense.
Yes. Yeah.
So I mean, like if we
So you're asking, what does it tell us that the majority of them depend on all the axioms? What does that say? Is that the question?
That's one question, but I mean, I think the general question, let's see, distance matrix would give us the whole distance matrix here. And then we'd say, what the hell is that? Or is this graph distance matrix? Oh, there we go. So let's say we say, array plot or matrix plot. The hell do we conclude from that?
I don't know.
Well, nor do I. Let's see if we don't.
I'm not sure what to make of that.
That's a lot of infinities.
Okay. Yes. Wow. Yeah.
Very useful. what the hell do we conclude from this? I mean, we've got this graph. We're trying to discuss whether there's uniformity, for example, in metamathematical space. So we can start to ask questions like, is every light cone, how similar are the light cones? I suppose is one question we can ask. How connected is everything? Well, it's all connected. Okay.
So if they share all those 10 axioms, you could make those 10 axioms the seed of an entailment cone, and then 55% of those are going to be in that entailment. But then, well, but then the other ones,
it's kind of obvious that
the other ones will be in there too. They just don't depend on all of them. What does the fact that they depend on all of them tell us? What does that tell us? What do we get from that?
That a reference frame that does not contain all of them,
yes,
won't get all of Euclid.
Right. So if you have entailment cones where the seedlings of those entailment cones don't include all of those axioms, you might get some theorems, but you're not going to get 55%. 55% have to be in the entailment cone that has all 10 in the seed.
Hold on. If the entailment cone of each axiom on its own, won't get much.
That's right.
Needs overlaps to get Euclid. But what does it mean that these, I mean, what do we conclude from the big mess that is this? And what do we conclude from the fact that,
well, this graph is messy and difficult to interpret. I mean, I can think about this statistic you have here. I'm not sure what to make of the graph. It's hard. It's not easy to read it.
Well, I know, but I mean, it's
the matrix plot reveals something about the order of theorems, right? Because each of those squares, because they like bulge up a little bit. It's like one particular theorem, right? Because it basically contains some axioms that are very close to each other. If you just make a random sample of those and make a matrix plot again.
Random sample of what? Like a random graph?
Yeah, because like adjacency matrix or graph distances, like the order of vertices is arbitrary, right?
Yeah.
Or maybe it was like in some kind of.
No, it's in a definite order. It's a definite order. Look at these.
Yeah, that's why this reveals as the actual order. If you just random sample it, there's not going to be any squares and sizes of squares.
Yeah, no doubt. But so what? I mean,
or at least some substructures are identifiable.
Yeah, I mean, there's a certain amount of clumping. You know, I talk above about how, in this case, I describe notable theorems staking out separated territories in the entailment cone.
Yes.
You know, I don't know how true that is, but it's you know, you can see these ones over here are separated from the ones over here.
Yeah, that's hard.
What's that?
Maybe just this particular layout.
Well, I know.
That's why it's hard to analyze these, right?
Yeah.
Exactly.
Well, you see the same thing in other layouts, by the way.
clumping,
Yes.
or those clusters, because they have high connectivity between them.
Yes.
Yeah.
And those are very similar theorems.
Right.
And I think most of these theorems go all the way back to the axioms to prove themselves. Which is not true of Euclid. I mean, Euclid, oh gosh. I mean, Euclid, those are causal graphs. What really depends on what? So that's the number of axioms used. Of the 1024 possible subsets, only 19 subsets occur. Okay, the question is what on earth to conclude from this? I mean, so one more moment on this, okay? So, you know, what we're trying to do is get evidence of physicalized mathematics. Why is this, you know, there are enough axioms, I mean, there are far fewer here than there are on the MetaMath database, okay?
Correct, yes.
But this is kind of a test of, I mean, we're going to get the same kind of picture for the MetaMath database, except it's more complicated.
Yes, we saw in the graph or the grid yesterday that many of those theorems depend on all the axioms or almost all.
No, I know. But the question is here, okay, the question is we're trying to understand, you know, how do we get evidence for physicalized mathematics? We want to find things like the uniformity of mathematical space. How do we measure that from here?
We're not going to get that.
Why not?
Look, it's uniform in the Rulliad. It's not going to be uniform for the observer. Like we've discussed this yesterday. We've discussed this many times.
I'm not sure it's true. I'm not sure it's true. I'm not sure that Euclid.
If it was uniform, if it was actually uniform for the working mathematician, wouldn't mathematics be, in a sense, kind of less trivial than it is, or sorry, more trivial than it is today? I mean, it would be easy. A lot of these open problems would be solved. You'd be able to translate.
There wouldn't be an open. There wouldn't be an open gap in somewhere. But the question is, how do we represent this picture in terms of how uniform? You know, it's like, how do we represent the uniformity or not of mathematical space from this picture? Is it the branch shield graph, or what is it?
Well, okay, this is a good question. Yeah, the dependency on the axiom seems important in this respect. So let's think about the dependency on these common axioms and what that means, what that would look like branchially. Right.
Well,
so these theorems,
eventually connecting, going all the way back to the Big Bang, it means that everything is connected. They all have common light cones. Going back to the Big Bang.
Yes.
Okay, so I mean, it's like
so it's locally, maybe in some sense, in some local sense, it is uniform in some way if they're connected like that.
Okay, so it's not the case that different parts of the mathematical universe are disconnected. Because they come, you know, by coming from different axioms. So that's one interesting fact. There aren't very many event horizons.
Right.
Okay, but so
Yeah.
now if we go to a different layer of the branch hill graph.
Can we take the branch hill graph of this?
Yes, we can. I did it, of course. There it is.
You're sure that's this exact graph?
Yeah.
Okay. Okay. Yep. There it is. Okay.
Well, it may be of the transitive reduction. Let's see. Corresponding transitive reduction graph. You know, this might be of the transitive reduction graph. So let me just see here. The hell is that? I don't understand that. Parallel map. I mean, we've got this graph. It's called EUC. And Nick's branch hill graph computer should give it to us. There's the thing.
Yeah.
Not as a layered graph, but
Yeah. So let's take branch hill graph of it.
okay. How do we do that?
Lowercase b branch hill graph.
I see that like it computed the layers based on the longest path. I've also done something like that.
Why is this taking forever?
We're trying hypergraphs.
What?
What is the number 2 there?
Well, I thought I was supposed to be getting 2 layers. What does this exactly compute? Oh,
Just computes ancestral dependency between every vertex.
Okay, but that's 465 squared vertices. It's 465 squared. Okay.
Interesting.
So we can probably label this. That's amusing. That's quite amusing. That's number theory. That's plane geometry, and that's 3D geometry.
Interesting.
Why do you have this vertex labels, arrow vertex labels?
Yeah.
Well, that would be why we don't have vertex labels here.
Okay. Okay.
So this is, what is this representing? This is representing any level of ancestral connection.
I mean, is this metamathematical space? Yeah.
Should be.
Okay, well, what can we do to assay uniformity further with this? We have this. What else can we do with it?
Well, how else could we display this thing? I mean,
well, there's that. Sure.
A hyperbolic thing would be good. I mean, I suppose I could take this and make a graph 3D out of it. Let's skip the labels.
Mm-hmm. Okay.
Welcome to mathematical space. I mean, it is interesting that these things.
Yeah. This little number theoretical grapevine.
Blueberry. Yeah.
Yes. Yeah. Right. Exactly.
I mean, that's to be compared with this. Which is the direct references between books in Euclid. Is this the direct references or is this arbitrarily indirect?
I don't remember.
Well, but Nick, what is this Brancho graph actually showing us? It's the first level ancestral connections or multi-level ancestral connections?
One level. So the two vertices are connected if they have a common ancestor, immediate one.
Okay. Why would the axioms even be on here? Because they have no ancestors.
I don't know. Guess this is. We can check. Are you sure that they don't have any ancestors?
Yeah.
Then this is weird.
I mean, here, CN4. Look, the fact is 1.7 depends on many things. I don't know what it means to have an ancestor because 1.7, right? Let's look at 1.7's graph. Okay, CN4.
Is there?
There isn't there. CN4 isn't there.
Oh, I see. Yes, no. I was looking at the Brancho graph. It's not there. So wow. No, got it.
Why is it in this thing? I mean,
the others too.
Well, this is the out component, right? Of your 1.7. Can you try and
you know what? Big problem. We need to reverse
the whole graph, right? Right.
then your axiom's gonna make like one disconnected branch of piece.
Yeah. Why is this taking much longer?
Okay.
Okay, that honestly seems more plausible. There are no axioms visible here.
I guess I dropped them. Because I remember I have an option that includes whether to include those things, right? Or what is this?
Look, I dropped the, I mean, this was my branch graph from the Boolean algebra stuff above. Maybe that's more relevant than I thought it was.
Why didn't you think it was relevant?
Because I wasn't sure what it meant.
Do you know what it means now?
Actually, I think this supports my claim about clumps
Yeah.
of notable theorems.
Well, obviously, look at it. Yeah. But we noticed that since the beginning. No?
Somewhat.
Yes.
I mean,
look, when I see this graph, it's like you don't have smooth metamathematical space, but you do have local, highly connected patches, which kind of sounds like mathematics today. There's some connection. There are a couple of freeways you
yeah, I
can
know,
take.
but remember, this isn't. Yeah, this isn't the full entailment cone. This is just the entailment cone from these particular theorems. Actually, you know what we should do? We know what we should do.
Yeah.
We should make the analogous graph including many other true theorems that aren't named.
There's an idea.
Right. And then,
Right.
so then what we'll get is something where we'll see the named pieces, you know, how uniform are the named pieces in the space of all possible pieces. All right. I think we're getting something to say here. I mean, this is and this is sort of the, that's the first level connection. And this is kind of the, yeah, is there a way of doing two-level branch hill graphs?
That would be a hypergraph.
Well, unless we squash it into a, by the way, here, presumably, we want to say, if we say edge style arrow, is it going to be,
For a graph like this, if it's going to be that size, is it helpful for it to be labeled?
well, if you know your Euclid, it is.
But you can't see the graph.
I know. Well, oh, I see, because it's got too much black stuff in it. Well,
Yeah.
I agree that that's a problem.
Huh.
Well, let's get rid of the labeling.
Yeah.
And we've also got to make those branch hill colored, but
Well, this might give us an opportunity to really look at the structure here. Let's see.
Why isn't this coming up? Oh, there we go.
Still a little hard to.
Not hopelessly hard. I mean, it's not.
Oh, this is nice.
I mean, this is essentially a reconstruction of mathematical space from Euclid.
Yes. Wait, you mean branchial edge coloring? Yeah. Okay.
So the basic point here, the hell is the basic point? The basic point is that there are pieces of Euclid out here book 7 and book 9. Book 7, book 9. That's that proboscis.
Yes. This is nice. You can actually kind of see the correspondence between these.
Yeah.
Oh, that's really cool. Yes, and book 10 is like a bustling city.
Yeah, but it's not that surprising because this is the direct connections between, I mean, it's a slightly different way of measuring this.
No, it's not surprising. It's just nice. It's nice to see.
Yeah. But I mean, this is okay. So this is that reconstructed thing. So if we're lucky enough, we could probably do this for 1 second, and then we're going to get to your stuff. So this graph here is the result of those particular theorems. Okay. Okay, so here, well, what I did here, oh, I see. I did a graph union of the proof object to this thing. And here, okay, so what I'm doing here, I've got these theorems. So I've got A, B, C. Truth is that these theorems will be enough, actually. These theorems are definitely enough because I've got the ABC theorems here. I don't quite have up to that level, but it's close. Oh, for goodness sake, where's data 53? That's uninspiring. I don't know what data 53 is.
Is this from the click to copy? Like if I try to do the click to copy for this, am I not going to be able to run it because it has a dependency somewhere else?
Yes, if we didn't
this
get
is
fixed.
This is why we have to do the C2C audit. We definitely have to do this audit.
Yeah, because it's a big mess.
Yeah.
I mean, no, it's not even close. There's tons of stuff that is sloppily done here, like that. Okay, tons and tons of stuff.
I know.
That one there is No, actually. That's this thing there. Oh, for God's sake. That's really annoying.
Where is it?
Well, it's probably, oh, it might be in there. It might be in there. Okay. Call off the dogs.
It's not helpful though. No one's gonna know that. No one
Well,
outside of
if you
Wolfram's
run
gonna
it,
know
if you
that.
run it, it's going to work.
No,
Now,
no,
I
but
know that's why I'm trying to get rid of those cloud gets. It's exactly why I'm trying to get rid of the cloud gets.
Yes.
Okay, so if I say here / dot v goes to the OR symbol, which is the circle plus, wedge goes to circle times, and square goes to overbar. Okay, so now these are a bunch of theorems, and then what we're going to do is just indicate those theorems. See, the thing is, what we'll get here is a big nest. Actually, this is a really nice thing to do. This is really going to show us where those theorems are in the space of all possible theorems. Okay, so if we say...
That's what we've been looking for. Yeah, okay.
Well, I mean, it's only approximate because it has some... Okay, well, these are this might be slightly funky, but it's okay. Let's take 100 of them or something. So here, we're going to get okay, so I was using this hack here to figure out whether they were original theorems. Well, I can just, those theorems would actually be like that. And there'll be a bunch of things with X's in them. Okay, so here, let's just do this. And then let's say, okay, lovely. That's kind of cool, actually.
Good.
Okay, so now we say graph union of just those.
Okay.
Okay.
Whoa.
No, that's what we'd expect. I mean, this looks very similar to that as well. But the issue is, so what we want to do is we want to get a decent number of these. And then let's just say 200 of these. Background is this. Okay, now that might include some of these. We really want to remove those theorems. Well, no, it doesn't really matter. We'll want to take those. The background is this. Okay.
What's cool about that layout is you just see how many holes there are in it. You can't really tell when you have the other layout.
Yeah,
I
no,
guess
I
you
agree.
can kind of tell.
Is it also like takes a union of lemmas?
Yes.
Kind of weird, right? Because they're different.
Why are they different?
Well, because it's like a simple label, like substitution lemma 1. In all of those proofs, substitution lemma 1 are different.
Oh, how do we get rid of those? How do we?
I would just like vertex replace.
No, we don't. What isn't there a way of just removing the
events.
events, yeah.
Yeah, well, we can remove events. Yeah,
How do we do that?
remove events from each token line graph.
Okay, so then we just say remove events / @background, and then we say graph union
It's quite different.
Yeah, I mean, this thing probably should have its remove events done.
Yep.
Yeah, this is very different.
Let's just do this with remove events. Okay, so then we say remove events.
Or maybe, arguably, events shouldn't be removed, but just unified, basically, for each of the individual proof. Depends what you want. Okay, it's nice.
So what does that show? That shows there's big clusters of theorems here.
Yeah.
Okay, without events. But if we unified the events, how would we do that? For each thing, we would say, instead of that, we would just say vertex. We just replace them all by a UUID. Right, so we could just say here, take this, and we replace the events. So we would do here, instead of remove events, we would say vertex replace of hash, comma, and then everything that is of an event type, event blank blank. Is this going to work?
Yeah, sure.
Okay, so what should we do? So we say create UUID.
Maybe. Yep.
So that's a more accurate version of this with different events, which didn't get properly colored, but those, if they were colored, those would just be different events.
Well, maybe just make list event create UUID.
What? I did that here.
No, I mean on the right hand side, so that it also inherit the style.
I don't think it's still correctly inheriting the style. Okay, but I agree that that would work better. Did I get that right? Vertex style, list comma orange.
Yeah, that should work. Only events are lists if you make it like this way.
That's nice. That's showing lemmas and that's showing the actual theorems. So now here, move this down. Okay, so here we've got the background. Oops. Background is there. And then we're going to say, let's do remove events initially. Okay, so this will be graph union of remove events of this thing. Graph reunion of remove events of background. Now the question is to include. So we've now also got po union here from po list, which is those particular events there. Okay, so now we want to say, oh no, what we would want to do is to say graph union of we want both of those things. So we say join. Does graph union takes, yeah, it's at. Join, remove events of po list, and remove events of background. And now we want to color the particular, these axioms here, these things here. So we want to say, how do we do that? We want to make those things, we say, in that, we say graph of that. And then we say vertex style arrow thread this thing arrow red. Do you agree?
Well, yep.
Oh, look at that. Well, what do you know? The background doesn't quite reach far enough. That's really cool. So that's showing in this graph, not a branchial graph, but this is the in this graph. Well, let's just see if we did all the full data 53. Or we might have to go further than data 53. Then I want to see your stuff. Ta-da! What the hell is that? I mean, there are things here, but they're very peripheral. Now, presumably, we could also make a branchial graph from this.
Why not?
Yeah. Well, like what are those eyes?
I don't know. I mean, those must be theorems that are, those must be lemmas that just keep on being used. You know, I have a feeling we're going to see as much.
But haven't you removed the events?
Yes.
So they're not lemmas.
They are lemmas. They're lemmas because they're theorems. They're theorems that are connected to other theorems. Let's do the version without removing the events.
Nick usually refers to the events as the lemmas. Have I missed something?
I don't like it. It's how proof object refers to them. It's like,
yeah, but it's wrong.
Yeah,
these are the lemmas. These are the lemmas. The things, blue things are the lemmas.
Okay. So sometimes we call the tokens
Okay.
theorems. Sometimes you're calling them lemmas.
Yeah, well, lemmas and theorems are the same thing. I mean,
Mm.
yeah, the lemma is just a theorem that didn't raise to the level of being named.
I see. And the token doesn't care about that. Right. Yeah, fair enough.
I think this is showing the theorem prover. I think it's showing what's happening in the theorem prover. But hold on, let me just make a version of this that is let's say take background, comma 200. Yeah, it's a bit more civilized. It's starting to develop the eyes.
Do you think, I mean, it might still be a good idea to take the branchable graph of the full one.
Yeah, I agree. But I mean, well, also we should do the thing with, okay, so here we might even be able to label the things.
Maybe those eyes are commutativity for or and end. That would be my guess.
Okay, let's see if we can see the eyes. Oh, you might be right. There it is. There's commutativity. We also should have marked the axioms on here, which we didn't do.
Well, this also contains those x's. Annoying. Maybe you should canonicalize symbols.
Right.
Yes, the eyes are probably commutativity. Let's see, what was the other point we were just making? Oh yeah, we should. Yes, and canonicalization of symbols.
Yes.
Which we could do. Is there a way of doing that for a whole graph?
I have canonicalized symbols, just takes a list of symbols and expression. So maybe you just...
Yeah, I know, but then we have to do vertex replace on the graph. This is one of these cases where, you know, the fact is if one shows this picture, it sort of supports the text. The only problem is the picture is a fake. Do you understand what I'm saying?
Well, we shouldn't do that.
We're not going to do that. We're not going to do that.
Yeah.
I'm just pointing out the academic system.
Pointing out the, how should I say, the ethical choices available to us so that when we make a choice, we're aware of the alternatives that we've elected not to adopt, right?
Right, let's see, how do we make this kind of graph? The kind of graph where we're showing the theorems embedded when we actually have, okay, so we have to do this. We have to do these basically. I just want to make one with the events. And this is background. Why is that going so slowly? That's really odd. See how slowly that's going? I mean, it's a huge number of independent vertices. I think that's not a good idea. All right, let's see your stuff, and then we should continue this tomorrow. Okay, do you want to share your screen, or should I open something here?
Yeah, Nick, why don't you serve as the guide?
Oh, no, maybe it's easier to open. It's in
Okay,
mathematics. We have it in the.
Yeah. By the way, I did notice that
open
you
it.
were. Which one?
Did you have trouble with 82?
No, 82 got overwritten while I was messing with it. I mean, that's the point. You took 82. You should have made it 82A or something, so that your new stuff was in a different file. No matter. Okay. So where is it? What's that?
I didn't rename it. I think I renamed it.
Okay.
Sorry. Okay.
Well, wait a minute. What did you rename it? Because this doesn't have new stuff in it.
Where is the new stuff? 82 empirical.
That's the
what
one I'm looking
has. Yeah.
But it doesn't have new stuff in it.
Yes, it does.
Oh, what's that? Yes, it does. There it is. Okay. All right. I haven't seen this.
Yeah. Well, yeah, even that's new.
What's new about this?
It has 14 new theorems and 1 new axiom.
Oh, so you fixed the math
Yeah.
Okay,
Yeah.
so but I mean the real. Oh wow, that's going to be exciting.
You just.
I know. I went to, but is this the new version of this?
No, we haven't done that yet. We've
Yes.
been working on the cloud. It is
Up to this. Yeah, before this colorful one, everything is new.
Yeah, but this is new.
Okay. All right. So we have to make
We
the colorful
didn't
one.
run this one, but
Yes.
above it.
Yes,
above.
that's new. The other one hasn't been done yet. Yeah.
What are these theorems it doesn't depend on? Axioms it doesn't depend on. Schroeder-Bernstein. Cantor's theorem.
Cantor is actually kind of a parsimonious theorem.
Principle of mathematical induction. I see. So those probably don't depend on some set theory things. What the hell depends on that? The partition theorem by Euler depends on this.
Yeah. Axiom of choice.
How weird. It's the only theorem that depends on the axiom of choice.
Well, no, it's the only theorem that depends on this particular version of the axiom of choice. You see, it's AC2. There's another one in MetaMath.
Well, but it's not in this list. So
It's
What,
C-
AC isn't anywhere? I can't see. It's too small. Hold on.
No, AC is not in that list. Okay, all right, let's go see this thing here. Okay, so Pythig. What's Pythig and Pythag? Oh, Pithy graph and Pythag graph.
Yes.
Yep.
Okay, so what are these? These are two different versions of,
Pythagorean theorem. Two different proofs.
yeah. No, they're not two different proofs. They're two different, aren't they two different theorems?
Sorry, they're two different theorems, but they have their own respective proofs.
yeah, one of them is general.
Okay. And so here,
Yeah, look at this.
what the hell is this?
Yeah, look at this.
What is this?
This is the number of times the axioms are used.
My
For each
God.
axiom, I know. For each axiom in the graph.
Yeah, if you like expand it, the full graph, make it into a tree, then that's how many leaves it's gonna be in that tree, I guess.
Isn't that big?
That's cut elimination, basically. Is that right?
No, I don't think so.
Why not? Isn't that going back to the axioms every time? As opposed to having intermediate lemmas.
No, maybe, yeah. Well, yes. Then it is like cut elimination.
So what did you work out here? So this is the number of individual this is the various axioms, you know, so this is 10 to the 26 axioms. Let's see.
That
means
it's that axioms isn't it? The axioms use 10 to the 26.
Which axiom? I don't see an axiom here. Oh, Pythi axioms.
What if you put your cursor over it? Does it tell you?
No, I mean Pythi axioms there. Pythi axioms is the vertex list of the vertex out component graph. I don't quite understand that. I mean that's.
Look, Nick.
Oh, I see. Which would start with axiom or definition. Okay, fine. So this is what you get if you unroll all the sub-dependencies, which are sub-dependencies. Right. It's not using the DAG. It's using a tree instead of the DAG, right? To evaluate.
A DAG, but it's recursively sums.
I know you're using a DAG. I know you didn't have 10 to the 26 elements. You're using a DAG, and you solved the problem that we talked about yesterday of recursively summing. But this is as if a tree. If you unrolled the DAG into a tree, the tree would have 10 to the 26 elements.
Yeah.
Is that true?
Yep.
Well, that is pretty interesting. That is pretty interesting.
I mean, that's the outlier. What's also interesting is that there's a significant number of axioms that are still called like 10 to the 14
times.
In the case of Pythag. For Pythag,
right. So the question is, which axiom is called 10 to the 28 times?
Well, we can get that. We can get that information.
Yeah, I know. Okay, so let me just understand what this is showing. So this is showing, I mean, I've got this information for Euclid of how many times each axiom, we need to work it out specifically for Pythag in Euclid, how many times each axiom is accessed there. But, you know, the answer for Euclid gets up into the hundreds of thousands. I didn't have an efficient algorithm for it, although I knew there could be one. I just brute forced the thing, pretty much.
Well, look at it. It's like almost one line.
I knew it was going to be one line. I just didn't write the one line. Well, Mano actually worked on that piece. And I thought it's very nice that it's one line. And probably it should turn into a WFR thing.
That's kind of interesting. Nick had this idea of basically using an analog of maximum flow.
Yes, that was kind of.
But it's not quite maximum flow. It's slightly tweaked.
Yeah, I mean, this is quintessential like programming competition type. You know, that's very nice. That's one line is very nice. I mean, that's the kind of code where somebody can actually understand what it does. Okay, but anyway, so what this is showing is we've got Pythag has this, you know, huge dependency. Okay, now what are you about to show? You're about to show, what is this thing here? What's this thing here? Is that the common? Those are the
in definitions.
Okay. So those are the leaves for each one, and that's the number of leaves in common. And now you also had this fancy picture. What is this?
It's the cloud.
Well,
they're the two graphs. They're the two graphs, and they have a green intersection.
And what the hell does this mean?
Well, it means they're not separate, which is what you conjectured yesterday. They actually do have an intersection, which is somewhat sensitive.
Well, in other words, this generalized Pythagorean theorem and the other Pythagorean theorem have a lot of common math in them.
Yeah, but they're also they also have non-trivial complement, which is interesting as well.
Well, what I suspect is happening is that, there's all kinds of stuff about complex numbers, but then in the end, it's turning down into things about, order relations and God knows what else, which are all in common. See, the thing that would be our true shreddable observer, well, is this a shreddable observer story?
Could be a destructive interference story. Not sure.
No, I don't think so. I think the point is the shreddable observer is you've got Pythagorean theorems, you've got two Pythagorean theorems,
Yeah.
and they have different foundational axioms. That was kind of the original concept. Now, this isn't quite that, because, and honestly, the shreddability in that case, the different axioms underneath really don't join up until they get to the EAM level.
Yeah. Isn't that what we mean by destructive interference? Like, let's say you presume both theorems to be, equivalent, right? But then halfway there, when you're proving them, you're in completely different parts of metamathematical space. That's basically definitional destructive interference.
Let me think about that for a second. That's an interesting claim. Okay, so what you're saying is there are two foundations for the Pythagorean theorem.
At least.
And yeah, I understand, but let's take two of them. Okay.
Yeah.
Which by the time we're at the level, okay, but both at the level of fluid dynamics, at the highest level, they act the same.
It's the same thing. That's right.
And at the lowest level, they also act the same. And you say, at an intermediate level, they're completely different. And what happens when the mathematical observer tries to encompass both of them? They get totally confused. What happens when the mathematical observer gets confused? They conclude I think the most likely thing is they conclude there is no true theorem here, or that it's somehow, because they're being sent to these two different ends. Look, the basic point would be that the principle of explosion, they think that they're seeing the principle of explosion.
But it's actually just multi-computational irreducibility and the uncertainty that comes from that.
Okay, so that's a very interesting idea. So the basic point is that we don't have a thing about this, do we? Oh my gosh, we took out the section on quantum effects. Well,
what?
Well, we didn't write it. It's not here. But we talk about it in topology of proof space, but we don't really groove on the whole quantum mechanics thing.
Well, okay.
Because we are merely starting a field. We're not finishing the field.
Yeah, I know. We're gonna get to 100.
No, I'm really trying not to.
I thought you wanted to. I mean,
well, I was
it would be nice to have the result, but we don't want to protract the actual writing process, because that's what's necessary in order to actually get 100, right? That's the point.
Yes. Okay. So anyway, but the basic point here is two Pythagorean theorems meet in whatever.
Yeah, right.
Two Pythagorean theorems, quotes join at the high level and at the EAM level.
So let's specify what that means. At the high level, it's just coarse graining on the part of the observer. Coarse
Yes.
graining that comes from naming. This is what you do when you name. When you name, basically you reduce a cloud to a point.
Yes.
Yes. Okay. Fine. And what about at the E
coarse,
level?
but hold on.
Yeah,
Coarse
okay.
graining. Okay. Well, I mean, okay, but
Well, it's not that you're giving the same name to all the elements, right? It's that it's just Pythag and Pythie, those graphs that are in the cloud, those graphs are both basically equated. And you make those into just one point yeah, and one of those other graphs.
Let's just write down the main thing that we concluded here, that at the intermediate stage, one can end up with very meta-mathematically distant pieces. So an observer conflating these will be confused that they are seeing the principle of explosion. So what will they then do? They'll say, what I'm seeing here must be false.
That this path equals this path can't be true. Right?
No, worse than that, that the original theorem can't be true, because as soon as you look at both of those things, if you took one path,
I think that's the same.
fine.
I think that's the same thing, right?
So what you were saying again?
Well, basically, if you don't think that those two paths converge, is that the same thing as saying that that theorem isn't true? In some way, I think it is.
Well, we're saying that the high-level theorem, that the Pythagorean theorem, is the conclusion would be, if you see both of those inconsistent proof paths, your conclusion would be the original theorem can't be true. So how does that manifest? That's close to something. That's saying,
look, it's like this. Someone gives you two paths. They tell you these both lead to the Pythagorean theorem, right? You're following these two paths, and in media res, they look completely different. You conclude there's no way these paths both lead to the same thing. I've been told that these two paths prove this thing. Therefore, I'm going to conclude that this theorem can't be proved, since these proofs that I've been given are probably bogus. You just don't have faith in the proofs.
Yeah, okay. So you believe the proofs won't converge. Given that they're so far apart, you believe the proofs won't converge.
Which, from a physical point of view, basically means you don't enjoy motion between them.
Yes. I think there's a different interpretation of this slightly. I mean, there are these books of 100 proofs of the Pythagorean theorem and things like that. And what does it mean that you can't continuously deform from one of those proofs to another? I mean, you're right, there's no motion from one proof to another. But what does that mean? I mean, we're all hung up on the double slit experiment and destructive interference there. But I think there's a different phenomenon. I think there's some phenomenon where...
Yes, I think it's multi-computational irreducibility. Not only do you not know what's going to happen along these paths, but you can't tell when these paths are going to start to indicate behavior that's going to be convergent. It's like thinking about computational irreducibility, but then comparing these different paths and looking at them at the same time. There's definitely no way you can translate between the two of them, but it's a different kind of irreducibility. It's not just straight down, it's a cross, so to speak.
That's interesting. That's kind of branchial computational irreducibility.
Yeah, you can think about it that way too. Which might have some quantum analog, maybe.
Well, yes, it's destructive interference.
Okay,
Can the paths be? That's a good way to say it, though. That's a good way to say it. Can the paths be brought together? That's a good way to say it. Branchial computational irreducibility. So that means that the proof paths. I need to go to sleep. The proof path. We got that discussion about multi-computation tomorrow, and
I have some questions about that before we wrap. Yeah.
Okay. Well, should we just talk about the administrative things for a minute, and then I got to go.
Okay. What's the objective or agenda for this